Alright, this video is for grade 11 regular chemistry with the organic chemistry section. We're going to focus in this video, it's going to be a bit of a long one, but we're going to focus on hydrocarbons, alkanes, cycloalkanes, alkenes, alkynes, and aromatics. Okay, so we're going to look at nomenclature. You'll see some molecules. I'm going to explain how to name them. If you're using this as a review, you can pause the video, try to name it yourself, and then check your answer to see how you're doing. If you're learning yet, then listen as I explain some of them, and then pause and try them on your own. Alright, so let's jump into this first one. So an alkane, you might remember that an alkane is a hydrocarbon where there are only carbon-carbon single bonds. So when you look at this molecule, all of the bonds in here are single carbon-carbon bonds. So that's what makes it an alkane. Now this particular representation is called a bond-line formula, So when we see a vertex like this, there's actually a carbon atom there. So there's a carbon atom here, a carbon atom here, a carbon atom here, and here. Now carbon, you might remember, needs to have 4 chemical bonds. So when you see this carbon right here, it has 1 bond to another carbon, so it needs 3 hydrogens to be attached to it as well to give it 4 bonds in all. Same thing with this carbon, it's got 1 bond to another carbon, so it has 3 hydrogens attached here. Now this carbon has 3 bonds to other carbons, so in fact that would be a carbon with a hydrogen attached. This carbon has 2 bonds already to other carbons, so this would be a CH2, 2 hydrogens attached. This carbon here has already got 3 bonds, so to get a 4th bond it needs 1 hydrogen attached. This carbon and this carbon each have 2 bonds, so these would be CH2s. They'd each have 2 hydrogens attached. So carbon always has 4 bonds. When you see a vertex like this, you think of it as a carbon, but you always remember that there's hydrogens attached as well. The number of hydrogens is the number equal to giving it 4 bonds in all. Okay? So if you wanted to give this guy a molecular formula, you could say it's got 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. This thing is C9. And then H, we could count them up, but you might remember the generic formula for an alkane is to take the number of carbons, double it, and add 2. So there should be 20. 2 times 9 is 18, plus 2. There should be 20 hydrogens in there. I want to double check. 3 plus 3 is 6, plus 1 is 7, plus 2 is 9, plus 1 is 10, plus 2 is 12, 14, and then 17 and 20. So C9H20 would be the formula. Now to get into its actual name, you first try to find the parent chain. The parent chain is the longest continuous chain of carbons in the molecule. So for this guy here, I think we have a choice. We could start down here, or we could start up here. It doesn't matter. This could be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. It looks to have 6 carbons in its longest continuous chain. So therefore, if we name that the parent chain, it's going to be called hexane, right? I'm assuming you know the first 10 names of the alkanes: methane, ethane, propane, butane, etc. So when you have 6 carbons, that's called hexane. Now, what we want to do next is start numbering. Now, I've already numbered them 1 to 6, but I realize I should have numbered it the other way around. Because when you number the parent chain, you want to number from the end closest to any branches. So this parent chain has got 2 branches, the way I've drawn it. It's got a branch here with 1 carbon, and it's got a branch here with 2 carbons. So the way I've numbered it is actually backwards. So this should be carbon 1, and this is carbon number 2. You start numbering at the end of the parent chain closest to the branching. So this way, this is carbon 2, this is carbon 3, carbon 4, carbon 5, carbon 6. There we go. So now that I've numbered them 1 to 6, I can see this is 2 methyl and then 4 ethyl. 2 carbons is an ethyl branch. When you put the name together, you put them alphabetically. So ethyl will come before methyl because E is before M. So this is going to be called 4-ethyl, 4-ethyl, -2-methyl. So there's an ethyl branch on carbon number 4. there's a methyl branch on carbon number 2, and then the parent name, which was 6 carbons, hexane. Okay, so 4-ethyl-2-methyl-hexane. All right, let's go a bit faster for this next one. The parent chain here, starting numbering at an end closest to the branch, so I'll start at this end. This is carbon 1, carbon 2, carbon 3, carbon 4. So that's a butane. And on carbon number 2, there's a single carbon branch, and that's called methyl. So this would be 2-methylbutane. 2-methylbutane. Now this third example, the carbons are joined together to form a ring. Okay, there's no open ends. It's just they're joined together in almost like a circle. In this case, it's a pentagon, and so there's 1, 2, 3, 4, 5 carbons. So when you've got them joined in a ring, you have what's called a cycloalkane, and you simply add the prefix cyclo at the front of the name. So if this had been 5 carbons, it would be called pentane, but with a ring like this, it's called cyclopentane. Okay, so 5 carbons in a ring, cyclopentane. Now, we've been talking about these alkanes. Just to take a look at one with a molecular model. Okay, this is from a model set. This is what an alkane actually looks like in terms of its shape and geometry, and you can see we're drawing them as though they're these flat molecules, two-dimensional. In fact, they're three-dimensional molecules that can twist and bend and turn all the time. When you look at a single carbon in there, you'll notice that the geometry is kind of interesting. Here's the carbon. It's got 1, 2, 3, 4 bonds, as I suggested. It's a little hard to see in the video, but those 4 bonds are forming what's called a tetrahedral geometry. The angle in between the hydrogen-carbon-hydrogen is bigger than 90 degrees. It's about 109.5 degrees. It's a tetrahedral bond angle. So you can think of it as a triangular-based pyramid, if you like, with the carbon atom at the center of the pyramid. And you've got, in this particular example, see if you can figure out what that guy's name would be. Okay, can you see there the carbons in the chain? What would be the name of this molecule? Well, you see it's only got single carbon-carbon bonds, so this would be an alkane. And it's got 1, 2, 3, 4 carbons in a parent chain, so this would be butane. And then over here, carbon number 2, there's a methyl branch, a single carbon branch. So this is 2-methylbutane. All right? So that's what an alkane molecule actually looks like. Now this next example, so you can pause and try yourself. So we've got a parent chain of 1, 2, 3, 4, 5 carbons. Now I started up here, you could easily have started down here, same idea, 1, 2, 3, 4, 5. So that's called pentane. And then on carbon number 2 and on carbon number 3, there are these methyl branches, single carbon branches. So I'm going to call this 2, 3, and because I've got 2 of them, I'm going to use the prefix di. Dimethyl, 2 methyls, and then 5 carbons pentane in the parent chain. So 2, 3, dimethylpentane, and dimethylpentane should all be one word. Okay, the next one, the longest continuous chain. I'll start down here. This looks rather symmetrical. So 1, 2, 3, 4, 5, 6. So this is again a hexane molecule. But on carbon number 3 and on carbon number 4, there are these branches with 2 carbons in them. A 2-carbon branch is called ethyl. Okay, methyl, ethyl, propyl. You just take the name of the alkane. Methane is a single carbon alkane. You drop the E and you drop the ane rather, and you add YL. So methane becomes methyl. Ethane, a 2-carbon hydrocarbon, becomes ethyl, and a 3-carbon would become propyl. So in this case, we have a 3 and a 4, so 3, 4, and again, there's 2 of them, so we'll use the prefix diethyl, and then 6 carbons, hexane. The The next example is again a cycloalkane. We see this ring of carbon atoms, but it's got branches on it. Now the number of carbons in the ring, 1, 2, 3, 4, 5, 6. So this is a cyclohexane. And in the branchings, these are all single carbon branches, so those are all methyl branches. There's 3 of them, so we'll call it trimethyl cyclohexane. But we have to describe where those branches are, so we have to number the atoms in the ring. Now we're going to start numbering at one of the branches. So one of these carbon atoms in the ring will be carbon number 1, either this guy, or this guy. Now which one you use as carbon number 1, the rule is to keep the numbering of all the branches as low as possible. So for example, if I were to start with this as a number 1, then I would go this way around the ring, so that this would be carbon 2 and 3 and 4. So carbon 1, 3, and 4, I'll just write that here, 1, 3, 4, if I start here and go this way. If I were to start here and go the other way, it would be 1, 2, 3, 4, and 5. And 1, 4, 5, those are bigger numbers than 1, 3, 4. So I would actually have to go clockwise. But is there a way to get smaller numbers than 1, 3, and 4? But what if I were to start at this carbon here, call that carbon number 1, call this carbon number 2, 3, and 4. So if I started this way, it would become 1, 2, and 4. So because you're trying to keep the numbering smallest, I'm going to use that as my numbering. Carbon 1, carbon 2, carbon 3, which doesn't have a branch, and carbon number 4. So this would be carbon 1, 2, and 4. So 1, 2, 4. There's 3 methyl branches, so the prefix will be trimethyl. And then 6 carbons in a ring, cyclohexane. So 1, 2, 4, trimethyl cyclohexane is the name of that molecule. All right, this next one is a very simple, straightforward molecule. Sometimes people can do the more complicated ones and then forget to do the very simple ones. So just a 2-carbon alkane with a bond like that is going to be ethane. Okay, methane, that's just memorizing the names. The 2 carbons is ethane. In this case, we have 1, 2, 3 carbons, so this would be propane. However, there is a branch here with a Cl, and Cl is a chlorine atom. So the chlorine atom is a halogen, and when you name it as a branch, its name changes to chloro. Bromine would be bromo, fluorine would be fluoro, iodine would become iodo, okay, if they're named as branches. So in this case, the chlorine atom is on the 2nd carbon in the propane molecule, so this is 2-chloropropane. 2-chloropropane. All right. This next one is rather long, a complicated looking molecule. Find the longest continuous chain and start numbering from the end closest to a branch. So I'm going to start numbering at the right-hand side, and I'll call this carbon 1, carbon 2, carbon 3, carbon 4, 5, I can go up 6, 7, or I can go down 6, 7, 8. So there's the longest continuous chain. So 8 carbons means its name is octane, the parent molecule, octane. Carbon number 2 and carbon number 3 have methyl branches on them. Carbon number 5 has an ethyl branch. It's got 2 carbons. So we're going to name them alphabetically, so ethyl will come before the methyls. There's 3 methyls, so we're going to call it trimethyl. But notice when you alphabetize, you actually don't focus on that prefix, the T. You focus just on the methyl. Now, in this case, it wouldn't matter, but you use the root ethyl and the root methyl when you're alphabetizing. If there's prefixes, di, tri, etc., you ignore those when you're alphabetizing. So the ethyl comes before the methyls, so this is going to be called 5-ethyl, and then 2, 3, 3. Because there's 2 methyls on carbon 3, we say 2, 3, 3. So dash 2, 3, 3. dash, there's 3 of them, so trimethyl, and then the longest chain was 8 carbons, so octane. So on carbon number 5, there's an ethyl branch. On carbons number 2 and 3, there are methyl branches, but there's 2 of the methyls on carbon 3 and 1 of them on carbon 2, and the longest chain is octane with 8 carbons. So you can see, as awkward as that name is, it's actually very descriptive. If you give me that name, I can easily draw the molecule for you. Alright, this next one is again a cycloalkane. It's got 4 carbons joined together in a ring. 4 is butane, so that would be cyclobutane. But there's these 2 branches with bromine atoms, and just like the chlorine earlier, we're changing the name from bromine to bromo. So to number the carbons in the ring, it doesn't, because they're symmetrical, it doesn't really matter here. This could be carbon 1, carbon 2, carbon 3. You must start at one of the branches. Whether we started here or here wouldn't matter. So this is carbon 1 and carbon 3. There are bromine branches. So 1, 3 dash dibromo, and then cyclobutane. Butane because it's got 4 carbons. Cyclobutane because they're joined in a ring. Alright, this next example, a little bit long and ugly looking. We're going to start numbering from the left-hand side because that would be closer to a branch, so it doesn't matter which of these you call carbon 1. I'll do it like this: carbon 1, carbon 2, carbon 3, 4, 5, 6, 7. So this is a heptane molecule. When there's branchings, there's 1, 2, 3, there's 4 branches, and they're all the same. They're all methyl branches, CH3s. So we're going to call it a tetramethyl. The prefix for 4 is tetra. And they're on carbon 2, 3, 4, and 5. So this will be 2, 3, 4, 5. And then tetra, to mean 4. Methyl, the branches all have 1 carbon, methyl. And the longest chain, the parent chain, was heptane. And tetramethylheptane is all one word. And finally, we have another alkane. There's only carbon-carbon single bonds. And in this case, the longest chain is 1, 2, 3, 4 carbons. So 4 carbons is a butane. Now, which end should I start numbering from? Technically, there's branches from this on carbon 2 if I go this way, or from carbon 2 if I go this way, so it appears that it doesn't matter. But we're going to name bromo before chloro, because alphabetizing B comes before C. Because I'm going to name the bromo first, and otherwise it doesn't matter, then I'm going to start numbering from this end. Carbon 1, carbon 2, carbon 3, carbon 4. And I'll call that 2 bromo, 3 chloro, and then 4 carbons in the parent chain, butane. Okay? 2 bromo, 3 chloro, butane. Alright, now, before we switch over to the alkenes, can you give some of the molecular formulas of these compounds? So, for example, this guy here, 2-chloropropane, it's got 1, 2, 3 carbon atoms. So we'll say C3. It's an alkane. So again, the general formula of an alkane was CnH2n plus 2. The number of hydrogens is twice the number of carbons plus 2. So coming down here, if this were just propane, it would be C3H8. 2 times 3 plus 2 is 8. But there's a chlorine that has replaced one of the hydrogens. So instead of H8, we'll get H7 and then a Cl attached. What about this really ugly thing here? Okay, now we can sit here and count carbons, but maybe we can just look at the name. Octane has 8 carbons. There are 3 methyl branches, and those are single carbons, so 8 plus 3 is 11. And then there's an ethyl branch, one of them, which has 2 carbons. So 8 plus 3 is 11, plus 2 more. This thing has 13 carbons, C13. Now you could just count them. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Once you figured out there's 13 carbons, then the number of hydrogens is straightforward. It's twice the number of carbons plus 2 more. So C13H28. Okay. Now what about 2-methylbutane? Can you figure out its chemical formula, its molecular formula? Well, 1, 2, 3, 4, 5 carbons in total. So C5. Notice butane has 4 carbons, and then the methyl branch has 1 carbon. 4 plus 1 is 5. And then twice that plus 2, C5H12. Now what about a cycloalkane? In order to make a cycloalkane, now here's cyclopentane, but let me just show you here. I've got cyclopentane built right here. To make cyclopentane with 5 carbons in a ring, to do that, imagine you started with pentane. Okay, so I've just got a 5-carbon alkane. In order to join the 2 carbons together to make the ring, I would have to remove a hydrogen from one atom and a hydrogen from the other atom at the other end of the chain. I have to remove 2 hydrogens in order to form this bond and close the ring. So if an alkane had twice the number of carbons plus 2 for its hydrogen atoms, but in a cycloalkane I had to remove 2 hydrogens, then the cycloalkane's formula wouldn't be 2n plus 2, it would be Cn and then H2n. Okay? Instead of the plus 2, it's just 2n, because we had to take away 2 hydrogens to join the carbons and make a ring. So with 5 carbons in a ring, this would be C5H10. Okay, coming down here, 6 carbons in a ring and 3 branches. So there's 9 carbons in all, so C9. But then to make the ring, you'd have to remove 2 hydrogens. So instead of C9H20, 2n plus 2, it's just C9H18, 2n. Okay? To make the ring, you have to take away 2 of the hydrogen atoms. All right? So this is just some looking at molecular formulas as well. All right. Now we're going to move from alkanes to alkenes. Alkenes, you remember, have double bonds in their molecules. Here's a very simple alkane. This is ethane with 2 carbons and a single bond. Notice if I want to make that single bond into a double bond, look what I have to do. I'll break the single bond, and I'll take that off of there. To make a double bond between these 2 carbons, I have to sort of do what we just talked about with the cycloalkane. I have to take away 2 of the hydrogen atoms. Now that I've taken away the 2 hydrogen atoms, I can take my 2 carbon atoms and I can join them in not a single bond, but a double bond. Okay, there we go. So there's a double bond between the 2 carbons. But to make that double bond, I had to take away 2 of its hydrogen atoms. So the molecular formula of an alkene is the same as that of a cycloalkane. It's CnH2n. So in this case, C2H4. Okay? All right, with that little aside, let's jump in. Alkenes, you remember, their names will end in -ene, E-N-E. Now in this first case, there's 1, 2, 3 carbons. So instead of propane, this is going to be called propene. Now, the double bond here is the first bond in the molecule. There's 2 bonds here, the first one. So some people would call this 1-propene, meaning the first bond is the double bond. However, if you put the double bond here instead of here, it would still be 1-propene because you would number from the end closest to that double bond. So because it doesn't matter where the double bond was, you don't really need to put a number in this example. You could just call it propene and that would be sufficient. The second example, though, is a little bit different. In fact, the second and third examples illustrate this. So this is 1, 2, 3, 4 carbons. So this is going to be a butene, 4 carbons, okay, with a double bond, so butene instead of butane. But does it matter where we put the double bond? In this case here, it's the first or the second bond, depending on, it doesn't matter which way you count, so first, second. So it's the second bond. But we could have put the double bond here or here, in which case it would be the first bond. So because there's two different ways to do it, we have to now tell you where we have this double bond. This one is the second bond, so we'll call it 2-butene. Okay, so this 2 is not referring to a carbon atom, it's referring to the bond that is the double bond. So the second bond in the molecule. Here's another one, which is also butene, 1, 2, 3, 4, so it's also butene, but this first bond is the double bond. So this one's going to be called 1-butene. So when you're naming an alkene, unless it is straightforward like this, where each bond here was the same, first, depending on where you put the double bond, you would just count from the opposite end. So these are both 1-butenes, no matter where you put the double bond, 1-propene. So you don't need that number 1. But over here, it does matter because this molecule and this molecule are different. So you have to tell me where the double bond is. Now notice if we had put the double bond here instead of over here, we would still call it 1-butene because you need to start counting from the end of the parent chain closest to the double bond. Now what if there are branches involved? Okay, here's an alkene with a branch. Well, we still start numbering from the end of the molecule closest to the double bond. Okay, the double bond takes priority over any branches. So in this case, we would start numbering from this end of the parent chain because that's closest to the double bond. So this would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. If it were an alkane, we would say hexane. Because it's an alkene, we'll say hexene. Now where is the double bond? It's not the first bond, it's the second bond. So this would be 2-hexene. And then on carbon number 2, there's a branch with 1 carbon in it. A 1-carbon branch is a methyl branch. So this is 2-methyl, a methyl branch on carbon number 2, dash 2-hexene. An alkene with a double bond, 6 carbons in the parent chain, hex, and the second bond is the double bond. So 2-methyl, 2-hexene. Now let me just point out that in this worksheet, we're not going to be discussing anything to do with cis or trans isomerism. So if you are more of an advanced chemistry student where you're looking at the geometry, the shapes of the molecules, you realize that some of these examples are the names I'm going to use won't quite be sufficient for an advanced chemistry class. All right, this next example is again an alkene. I see the double bond in there. And so we're going to start counting from the end of the parent chain closest to the double bond. So in this case, we'll start from the left. Carbon 1, carbon 2, carbon 3, 4, 5, 6. So this is again a hexene molecule. It's again 2-hexene because it's the second bond, which is the double bond. So it's 2-hexene. It's got methyl branches, but not just one, it's got 2 of them, and they're on carbons 4 and 5 in the parent chain. So we're going to call this 4, 5 dash 2 of them, so we'll use the prefix di, dimethyl, and then the parent chain was hexene, but it was the second bond, the double bond, so dash 2-hexene. Right, now what is its molecular formula? Well, the parent chain has 6 carbons. There's 2 branches with 1 carbon each, so there's 8 carbons in here. It's an alkene. So the alkene, the generic formula is CnH2n. So just twice the number of carbons. So H16 would be its molecular formula. Okay? This guy here, The parent chain, starting from the end closest to the double bond, this is again is an alkene. So this would be carbon 1, carbon 2, carbon 3, carbon 4, 5, 6, 7. Whether you went 5, 6, 7 or 5, 6, 7 doesn't matter. It'll be the same result. Now in this case with 7 carbons, the prefix will be hept. So this is a heptene, and it's the first, second, third bond, which is the double bond. So this will be 3-heptene. But on carbon number 5, there is a branch, and the branch here has 2 carbons in it. So a 2-carbon branch is ethyl. So this guy's name altogether would be 5-ethyl. There's the branch, dash, and now the parent chain with the third bond is the double bond, so 3-heptene. Okay, and alkenes, their names will always end in ene. There's a double bond present. This guy's molecular formula, heptene has 7 carbons, ethyl has 2 carbons, so this is C9, 7 plus 2, and then twice the number of carbons, H18. Down here, the parent chain, starting numbering closest to the double bond, 1, 2, 3, 4, 5. So this is a pentene, and it's the second bond in the molecule, which is the double bond, so it's a 2-pentene. And on carbon 2 and carbon 3, there are methyl branches. So this would be 2,3-dimethyl, 2 of the methyls, and then dash 2-pentene. Pentene, 5 carbon atoms, and the second bond in the chain is the double bond. This next one, even more complicated looking. The double bond is over here, so I'm going to start numbering from this end of the molecule, and it looks like I should start here. So 1, 2, 3, 4. We're trying to get the longest continuous chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 carbons. If that were just an alkane, its name would be decane. But because it's an alkene, its name will be decene. It's the first, second, third, fourth bond, which is the double bond. So 4-decene. And then we've got branches. We've got on carbon number 4, an ethyl branch with 2 carbons. And on carbon number 7, we have 2 methyl branches with 1 carbon each. We're going to name ethyl before we name methyl alphabetically. So putting it together, carbon number 4 has the ethyl branch, carbon number 7, 2 methyl branches, decene is our parent molecule, and it was the 4th bond, which was the double bond. So this is going to be called 4-ethyl dash 7, 7, there's 2 of them there, so we have to use the number twice, dimethyl, and then the 4th bond, so 4-decene. Okay, there's a pretty ugly name. 4-ethyl, 7,7-dimethyl, 4-decene. Its molecular formula, though, is not that hard. 10 carbons plus 2 more is 12, plus 2 more is 14. So C14, H28. I don't have to sit and count them because I know the generic formula of an alkene, CnH2n. Alright, this next one is a cycloalkene. It's got the 5-carbon ring again, so that's a pentene. If it were just an alkane, it would be cyclopentane. But there's this double bond, so that makes it an alkene, and its name is cyclopentene. Alright, now cyclopentene is actually probably going to be pretty unstable as a molecule, but it's possible to create that. Now, its chemical formula, it's got 5 carbons. Now you remember that to form a double bond, you need to take away 2 hydrogens, but to form a ring, you need to take away another 2 hydrogens. So instead of CnH2n plus 2, the generic alkane formula, CnH2n plus 2, we have to take away 4 hydrogens from there to make a double bond and a ring. So this would become CnH2n minus 2. If you want to take away 4 hydrogens, instead of a plus 2, you have a minus 2 now. So if there were 5 carbons, 2 times 5 is 10. Take away 2 is 8. So C5H8. Okay? When you have a ring, you take away 2 hydrogen atoms. When you form a double bond, you have to take away another 2 hydrogen atoms. All right, this next one, I see some bromo branches. I see a methyl branch. I see it's an alkene. Now, the double bond is at this end of the molecule, so we'll start numbering here. Carbon 1, carbon 2, 3, 4, 5, 6, 7, 8. So it's an octene. The first bond is the double bond, so it's 1 octene. Carbons 4 and 6 have bromo branches, so there'll be a 4,6 dibromo. And carbon 5 has a methyl branch, so 5-methyl. Bromo will come before methyl alphabetically, so this will be called 4,6 dibromo dash 5-methyl, and then the octene is the parent, and it was the first bond, which was our double bond, so dash 1 octene. That's chemical formula. 8 carbons plus 1 more is 9, so there's 9 carbons. It's an alkene, so C9 we would expect to have twice the number of hydrogens. We'd think H18, but 2 of the hydrogens have been replaced with bromines. So instead of H18, it's H16, and then there's those 2 bromines attached as well. And this last example of an alkene is again a cycloalkene. Okay, we see a ring, so it's a cycloalkene with a double bond, and it's got a branch, a methyl branch. Now, we have to tell where that branch is located, so we need to start numbering the ring. To number the ring, start at the end closest to the double bond. But the double bond, the 2 carbons in the double bond have to be carbons 1 and 2. Okay, the 2 carbons that make the double bond in the ring have to be carbons 1 and 2. So in this case, I'm going to call this carbon 1 and this carbon 2, and then this becomes carbon 3. If I had called this carbon 1 and this carbon 2, then we'd have to travel all the way around here to get to the methyl branch, and it'd be a much larger number here. So to keep the numbering smallest, and to keep the double bond as carbons 1 and 2, we do it like this, 1, 2, 3. So this guy's name is going to be 3-methyl. Now this should be one word, but I'm running out of space here. So 3-methyl, and then cyclohexene. Okay, there's its name, 3-methyl cyclohexene. All right. This next page, I realize this is a long video, but hopefully it's going to be a good review for you. So this next page is alkynes. You can see here all these molecules with triple bonds in them. When you make a triple bond, something interesting happens there. Notice that the shape of the molecule, the triple bond, forces you to take away 2 more hydrogen atoms, and then that leaves only 1 other branch coming off of each of the carbons where the triple bond is found. So the geometry here becomes a linear shape. So you have 2 carbons, something coming off here and something coming off here. In this particular example, see if you can tell what that molecule's name would be. It's got 1, 2, 3, 4, 5 carbons in a parent chain, so pentane, but it's got a triple bond, so this would make it an alkyne, A-L-K-Y-N-E. So instead of being pentane, its name becomes pentyne. Like the alkenes, we number from the end closest to the triple bond, so we number from this end over here. And then the bond with the triple bond is the second bond in. So the first, the second bond. So this is 2-pentyne. And then over here on carbon number 4, 1, 2, 3, 4, there's a methyl branch. So this is actually 4-methyl 2-pentyne. Okay? So there's an example of a molecular model that's an alkyne. All right, let's jump in. So the simplest alkyne has just 2 carbons. If it were an alkane, its name would be ethane. So as an alkyne, its name is ethyne. And now notice the generic formula for an alkyne, CnH2n. Instead of +2, like an alkane, we have to take away 4 hydrogens to make the extra 2 bonds there. So 2n minus 2 is the generic formula of an alkyne. So with 2 carbons, 2 times 2 is 4, minus 2, C2H2 is its molecular formula. Over here, we have 1 carbon, 2 carbons, 3 carbons. Okay, so the triple bond here is between this carbon and this carbon. So 1, 2, 3, this is propyne. You don't need to say 1 propyne, because whichever bond is the triple bond, that bond would become bond number 1. You know, if you did say 1 propyne, you probably wouldn't lose any marks for it, but you don't need to have a 1 in that case. This molecule here is a bit more complicated. 1, 2, 3, actually this is the one we just saw a minute ago in our model, wasn't it? 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. This is pentyne. 1, 2, 3, 4, 5. And on carbon number 4, there's a methyl branch. So this is 4-methyl. And then it's the second bond in, which is the triple bond, so dash 2-pentyne. Okay, that actually is the molecule that I showed you earlier, right? If I orient it the same way, that's what we have. So 5 carbons in a ring, 5 carbons in a parent chain, a triple bond as the second bond in, and a methyl branch on the 4th carbon of the parent chain. The next example, we start numbering from the end closest to the triple bond, so carbon 1, carbon 2, carbon 3, carbon 4, 5, 6. So this is a hexyne. It's the second bond, which is the triple bond, so this is 2-hexyne. And on carbon 4 and carbon 5, there are methyl branches. So this is going to be called 4,5-dimethyl dash 2-hexyne. 2 because it was the second bond that was the triple bond. Its formula, hexyne would have 6 carbons, dimethyl means 2 more, so C8, and then the generic formula, you remember, is 2n minus 2, so 2 times 8 is 16, take away 2 would be C8H14 as its molecular formula. This next guy, we'll start numbering from this end up at the top, closest to the triple bond. So carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and now it doesn't matter, I'll call this carbon 6 and 7. So that is a heptyne, okay, heptyne. And it's the 1-2-3rd bond, which is the triple bond, so it's a 3-heptyne. And on carbon number 5, there's this ethyl branch with 2 carbons. So this would be 5-ethyl dash 3-heptyne. Heptyne has 7 carbons, ethyl has 2 carbons, so this is C9, and then double that minus 2, C9H16 would be the formula. This next one has a chlorine atom as a branch, so it's going to have a chloro. It's got carbon 1, carbon 2, carbon 3, It's a propyne. We saw propyne earlier, but this time on carbon number 3 there is a chlorine branch, and you start numbering here because that's closer to the triple bond. So this will be 3-chloropropyne. Okay, and just like before, you don't need to say 1 propyne because there's only one place there to have the triple bond. This next example, starting numbering closer to the triple bond, 1, 2, 3, 4, let's see, 5, 6, 5, 6, 7, we'll go this way, 5, 6, 7. We want the longest continuous chain. So this is again a heptyne example, just like this one. And on carbon number 4, there's an ethyl branch with 2 carbons. On carbon number 5, there's a methyl branch. When I name those, I'll put the ethyl before methyl alphabetically. In the heptyne molecule, it's the second bond, which is the triple bond, so it'll be a 2-heptyne. So putting that all together, we're going to name ethyl first, then methyl, and then we'll name the parent chain. So this is 4-ethyl, ethyl branch on carbon 4, 5-methyl, methyl branch on carbon 5, and then 2-heptyne. 7 carbons with the second bond, the triple bond, and the parent chain. Its molecular formula, if you're interested, 7 carbons plus 1 is 8, plus 2 more is 10, C10, and then twice this, minus 2, would be C10H18. Alright, this next one is a even bigger, more complicated looking molecule. Number from the end closest to the triple bond. This is another alkyne. So 1, 2, 3, 4, 5, now let's see, 6, 7, 8 if I go this way, 6, 7, 8, 9 if I go this way. So 6, 7, 8, 9. We're trying to find the longest continuous chain of carbons. So this is the first time we've seen an example of 9 carbons. If it were an alkane, it would be nonane, okay, or nonane. In alkyne like this, it'll be nonine. It's the first, second, third bond, which is the triple bond, so it's 3-nonine. On carbon number 5, there's a branch here, which we haven't seen yet. This one's got 1, 2, 3 carbons. Now a 3-carbon alkane is propane, so a 3-carbon branch is propyl, P-R-O-P-Y-L. And on carbon number 6, there's a 2-carbon branch, ethyl. So naming the branches alphabetically, ethyl will come before propyl. So this is going to be called 6-ethyl dash 5-propyl, and then the nonine with the third bond, so dash 3-nonine. Okay? Just be glad your parents didn't call you that, right? Its chemical formula, molecular formula, 9 carbons plus 3 is 12, plus 2 is 14, so C14. And then for alkynes, you double the carbons and take away 2, so C26. Getting back to something a bit simpler, or maybe not. There's a bit of a trick here at the end. We see 1, 2, 3, 4 carbons, but there's this, instead of just CH3, the CHCl2. So that means there's 2 chlorines attached to that carbon. So I'm going to number that as carbon 1, carbon 2, carbon 3, carbon 4. This way the numbering of the branches will be lower than if I had started at this end. And in terms of the parent chain, it's a butene with 4 carbons and a triple bond. The triple bond is the second bond, so it's 2-butene. And on carbon 1, there's those 2 chlorine atoms. So this would be 1, 1. You have to use the number twice because there's more than 1. Dichloro. And then the parent chain, dash 2-butene. Okay? its molecular formula would be C4-butyne. Now, if it were just an alkyne, we would have H6 twice minus 2. But we've replaced 2 of the hydrogens with chlorines. So instead of H6, we'd have H4 and then Cl2. Okay, and you can actually see that there. There's 3 hydrogens plus 1 is our H4 and the Cl2. All right, one more alkyne, numbering from the end closest to the triple bond, carbon 1, carbon 2, carbon 3, 4, 5, 6, 7, 8. So this is another octyne. It is the second bond, which is the triple bond, so it's 2-octyne. Carbon 4 has an ethyl branch, and carbon number 5 has a methyl branch. So we're going to name the ethyl before the methyl alphabetically. So this should become 4-ethyl, 5-methyl, and then octyne, but it's the second bond, which was the triple bond, so 2-octyne. All right, and its chemical formula, molecular formula, 8 plus 1 is 9, plus 2 more is 11, C11, and then twice that minus 2 would be C11H2220. All right, so there's a bunch of alkyne examples. If you remember back at the beginning, we said this video would cover alkanes, cycloalkanes. We threw in a couple cycloalkenes as well, alkenes and alkynes, and so that leaves aromatics. Aromatics are a special type of organic molecule. They're usually described in introductory levels as molecules that are based on benzene. Benzene is the simplest aromatic molecule. It's shown here. That's just benzene is its name. And it kind of looks like cyclohexane. But there's a difference. In benzene, you have 6 carbons that make a ring, just like cyclohexane, but there's this what appears to be an alternating double, single, double, single, double, single bonds around the ring. Now, I say it appears like that your eyes aren't lying, but that's actually not quite how the molecule actually exists, because a double bond is stronger and shorter than a single bond. A triple bond is stronger and shorter than a double bond. If this were really single, double, single, double, single, double, like it suggests in this model, then you would expect to find a longer bond, a shorter bond, a longer bond, a shorter bond, etc. In fact, when they measured the bond lengths between the carbon atoms, it turns out they're all the same. And it's very hard to explain that when you're drawing the molecule like this with alternating single and double bonds like that, because that doesn't suggest that they're all the same. But what's going on there is something called a conjugated system of double and single bonds, this repeating pattern. Fancy word for that is conjugated. And the electrons that are in the double bonds here, turns out they're actually delocalized. To be localized means you're restricted to this one location. That in benzene, the double bond electrons are actually delocalized, and they're able to move around the ring. So sometimes benzene is represented as a hexagon with a circle in the middle, and that circle simply emphasizes that the bonds are not single, double, but rather that their electrons are moving around the ring, creating 6 bonds that are all the same lengths. Turns out they're a little bit longer than double bonds and a little bit shorter than single bonds. So that's what makes aromatic molecules different from all the other ones, and they form a special category. Okay, so that's benzene. The other aromatic examples here are going to be named as derivatives of benzene. So this next example, we see the benzene ring. So again, this tells me it's an aromatic molecule, and it's got 2 methyl branches. So we'll number them as carbon 1, carbon 2, carbon 3, keeping the numbers small. So 1 and 3 in the benzene ring have methyl branches. So 1, 3 dimethyl, and then we recognize this as benzene. And I didn't emphasize this, but notice here was our cycloalkane example, cyclopentane that I had earlier. Notice that each carbon in the ring had 2 hydrogen atoms coming off of it. But when you look at benzene, each carbon has only 1 hydrogen coming off of it. So the chemical formula for benzene is just C6H6. Okay? You could also figure that out because 6 carbons, if it were an alkane, would be C6H14, twice the number of carbons plus 2. But we have a ring, so we have to lose 2, and then we have 3 double bonds where we lose 2, 4, 6. So you have to lose 8 carbons from that. So if you take 14 minus 8, you'll get C6H6. But you could just memorize that benzene is C6H6. Each carbon has 1 hydrogen attached. So over here, with dimethylbenzene, this would actually be C678, C8, and then H. Let's count this up. The benzene would have had 6 hydrogens, but we've lost 2 of them to make those branches. So instead of 6, there's 4. And then we've got another 6 hydrogens over here, so C8H10. Okay? You won't really have to give molecular formulas for aromatic compounds, because they're a little bit harder to figure out. All right, the next example, we see again this benzene ring, which looks like cyclohexane, but it's different because it has this alternating single-double bond. So that's what you look for to say, hey, that's benzene. That makes it an aromatic molecule. They get that name aromatic, by the way, because when they first discovered them, the first few examples had pleasant-smelling odors. They had a nice aroma to them, so they called them aromatic molecules. Now, in this case, there's a methyl branch, and there's also an ethyl branch. So we're going to name the ethyl before the methyl alphabetically. And in this case, I'll start numbering here because I'm going to number the ethyl branch first, and I'll call it 1, 2, 3. If I had called it like this, 1, 2, 3, that would probably be also okay, but it doesn't really matter. There's going to be a 1 and a 3. But because I'm going to name the ethyl first, I'll call that number 1. So this is 1 ethyl dash 3 methyl, and then benzene. Now, the second and third examples were benzene rings with 2 branches on them. There's an alternate way to name them, an older name. The older name used prefixes ortho, meta, and para. So these prefixes are only used for benzene derivatives and only when there are 2 branches attached. If you have 2 branches that are side by side, 2 branches that are on neighboring carbons, so in this case it would be like calling it 1, 2 di something, then you could, instead of saying 1, 2 dichloro, you could simply say ortho-dichlorobenzene. If they're 1 carbon apart like this, carbon 1 and carbon 3 with a carbon in the middle, then you would say meta. So it'd be like 1, 3. So in this case, instead of calling it 1,3-dimethylbenzene, we could have called this meta-dichlorobenzene. And the meta would mean 1,3. Okay? Same thing down here. The ethyl and the methyl were separated by 1 carbon, so we could have called this meta-ethyl-methylbenzene. Okay? Meta, because they're in the 1,3 position. So meta-ethyl-methylbenzene would be its name using the older convention. In this case, we have 2 chlorine branches on a benzene ring, so this is going to be dichlorobenzene. And using the numbering system, we would call that carbon 1, 2, 3, 4. So this would be 1,4-dichlorobenzene. But using the older system, when you have two branches set on opposite sides of the ring, so with two carbons in between them, you could use para instead of 1,4. So instead of 1,4-dichlorobenzene, we could have called this para-dichlorobenzene. And sometimes it's very lazily, instead of even para, it'll just say p-dichlorobenzene. Instead of meta, it'll just say m-dichlorobenzene. And you would read that as meta. Okay? So again, ortho, meta, and para, those are replacing the numbers 1, 2, 1, 3, and 1, 4, only for benzene rings, and only when there's two branches like that. Okay? You can't use those in any other situations. So in this next example, there's 3 branches, so there's no way to use ortho, meta, or para in this example. So in this case, we have 3 methyl branches on a benzene ring. It's going to be trimethylbenzene. But we have to number to tell you where to put them. So how do I number them? Well, I want to keep the numbers as low as possible. If I were to call this carbon 1, then this would become carbon 3 and carbon 4, 1, 3, 4. But if I call this guy carbon 1, this guy carbon 2, and this guy carbon 4, instead of 1, 3, 4, we have 1, 2, 4, and that's slightly lower, so that's the way to number it. So this is going to become 1, 2, 4, the lowest possible numbering, and then trimethylbenzene. All right. This next one, again, benzene ring is an aromatic molecule. It's got 4 branches, so there's no way to use ortho, meta, or para for this. It's got bromo branches, and it's got methyl branches. So I'm going to name bromo first, because it's alphabetically before methyl. And now when we come to numbering, because we're going to number the bromo first, and there's symmetry here, in a way it wouldn't matter, but we'll call that carbon 1, this will be carbon 2, 3, 4, and 5. Notice if I had called this carbon 1, carbon 2, 4, 5, it wouldn't matter which bromine atom we started at. So I'm going to call this 1,4-dibromo, the bromo before the methyl, and then 2,5-dimethylbenzene. 1,4-dibromo, 2,5-dimethylbenzene. And 2 more examples, and we're done. So this next one, these are both benzene molecules, derivatives of benzene. So these are, again, aromatic molecules. This one has 2 branches, so we can use that ortho, meta, and para system if we like. In this case, the 2 branches are both ethyl branches, and they're on carbons 1 and 2. So the more proper way to do this would be call it 1,2-diethylbenzene. Okay? But 1 and 2, side by side, you could also call that ortho-diethylbenzene. Instead of writing out ortho, you could just put the letter O like I did there. So ortho-diethylbenzene or 1,2-diethylbenzene. And finally, the last example in this hour-long video. This one has a benzene ring with 3 branches on it, and there's an ethyl branch over here, and there's 2 methyl branches over here. We're going to name ethyl before the methyls, and we want to keep the numbering as low as possible. So how can we do that? Well, we've seen this earlier. If we call this carbon 1, carbon 2, carbon 4, that's the way to keep the numbering as low as possible. Carbon 1, 3, 5 1, 3, 4 would be a bigger numbering system than 1, 2, 4. So this will become 4-ethyl. You name the ethyl first, and then 1,2-dimethylbenzene. And because it's got more than 2 branches, we can't use that ortho, meta, para system. Okay? So there you have it, a whole bunch of examples of organic hydrocarbons. The saturated hydrocarbons, the ones with just single bonds, and unsaturated hydrocarbons where there's double bonds, triple bonds, etc. For grade 11 regular chemistry.